In this episode, we're going to be going over methods of evaluating classification algorithms. So the methods I'm planning to cover in this episode are accuracy, precision, false positive rate, recall, specificity, sensitivity, F1 score, and the UROC score. So for classification problems, we usually start out with some labeled data. So data that's either positive, in this case represented in green, or negative, represented in red. We put this data into a trained model, and this model either makes positive or negative predictions. Now, how do we evaluate this model's performance? So for this, we can look at what's called a confusion matrix. So where we made a positive prediction and the data point was actually positive, this is what's called a true positive. And when our model makes a negative prediction and the actual data point is negative, this is known as a true negative. If we get the positive prediction wrong, this is known as a false positive, and if we get the negative prediction wrong, this is known as a false negative. So if you guys have ever come across these terms before, such as true positive or false negative, try to remember that the positive or negative refers to the prediction made, and the true or false refers to whether the prediction made is correct. So in this case here, we have 3 true positives, 1 false positive, 2 false negatives, and 5 true negatives. So let's now go over our first evaluation metric, which is accuracy. Accuracy is concerned at looking at our model's performance on all of the data. So for this, we simply take the true positives and true negatives and divide it by the total. So in this case, it would be 3 plus 5 divided by 11, which is 8 over 11. Our next evaluation metric is precision. And for this, we are concerned about looking at our model's performance on positive predictions. We calculate precision by the number of true positives divided by the number of true positives plus false positives, which in this case is 3/4, which equals 0.75. So we'd want a high precision if we want to be confident in our positive predictions. So for example, in autonomous driving, a car must be certain when to turn left or right. And so the model built should have a very high precision. We also have the false positive rate, and for this case, a lower false positive rate indicates better model performance. And this is calculated by the number of false positives divided by the number of false positives plus true negatives, or you can just think of this as the number of false positives divided by the total number of negative points. So we'd want a low false positive rate if we wanted to ensure that every negative prediction is correct. We also have recall, and this evaluates our model's performance on positive data points. This is calculated by the number of true positives divided by the total number of positive points, which in this case is 3 over 5, which equals 0.6. So we'd want a high recall if we want a model not to miss positive points, i.e. we want a low number of false negatives. So in diagnosis, it's important that we have a high recall. So for example, if somebody has a certain disease or condition, we need to make sure that we detect those and we don't miss them. We also have specificity, and this evaluates our model's performance on negative data points, and is calculated by the number of true negatives divided by the number of negative points, which in this case is equal to 5 over 6. And we would want a high specificity if you want a model not to miss negative points. So this is the opposite as recall, where we do not want to miss positive points. We also have sensitivity, and this is just the same as recall. So we also have the F1 score that tries to combine both precision and recall into a single metric, and is calculated by the following formula: 2 times precision times recall divided by precision plus recall, which in this case is roughly 0.67. So here we're calculating what's called the harmonic mean of precision and recall. So the F1 score is quite a popular metric for evaluating classification algorithms, as it balances both our ability to confidently predict positive points, but also our ability not to miss any positive points. So our last evaluation metric is the UROC score, which is the area under the receiver operating characteristic curve. And the way that UROC works is by evaluating our model's performance on different decision boundaries, essentially shifting the decision boundary and then recording the true positive and false positive rate. So for example, in this case here, we're looking at our model's performance at a decision boundary of 0.5. And in this case, we get a true positive rate of 1 and a false positive rate of 0. And that's the best possible result that we can get. We see this orange line dashed along the middle here, and this represents the expected performance of a model if it was just a random classifier randomly predicting positive or negative data points. And for this, we would expect the true positive rate and false positive rate to be the same. So in this particular case here, where we're just evaluating our model's performance at a decision boundary of 0.5, we get a AUC score, or area under the curve score, of 1. And we simply get that by calculating the area under this square here, which is 1 times 1, which equals to 1. Usually we would evaluate our model's performance over different decision boundaries and then plot the respective true positive rate and false positive rate. So for example here, at a decision boundary of 0.3, we get a false positive rate of 0.55 and a true positive rate of 1, and we plot that on the graph. We then shift the decision boundary to 0.5 and then look at our model's false positive rate and true positive rate and plot that onto the graph as well. And lastly for 0.7. We then calculate the area under this curve here, and that gives us our UROC score, which is 0.82, indicating pretty good model performance. So that's it for this episode, and I hope you guys learned something new.